Hi everyone, welcome to the presentation of our work, GenSlice, Generalized Semantic Resizing. I'm Chen Guangzhu from UT Austin. This work is a collaboration with Yi from NTU, Julia from UBC, and Marsha from U Toronto. To show you what semantic history slicing is, let's start with the true story. What we are looking at here is a release note for the version 043 of the Bazel project. Bazel is an open-source multi-platform developed by Google. Here is how the development team cut releases. They have a master branch, which accumulates in incremental changes. Then they use the last stable version, in this case, the version 042, as a baseline. And then they manually cherry-pick commits they want in the new version to a release branch. After thorough regression testing, they then publish the release candidate and remove the release branch, carrying on with their work on the master branch. However, identifying commits relevant for high-level functionality from the version history is a hard problem. Let's see what the options are. First, we can pick the target commit, which we think is implementing the new feature. However, depending on the base version we choose, this often ends up being not sufficient due to the dependencies on earlier changes. We can also pick the entire history, which would include a lot of unwanted changes. Finally, manual cherry-picking is time-consuming and error-prone, because existing version control systems treat code as plain texts, and the user-created commits don't necessarily correspond to semantics of target functionality. Semantic history slicing is proposed to address these challenges. It takes a piece of history and a set of tests exercising the target functionality, automatically produce a subhistory which compiles and passes the same tests. This subhistory is called a semantic preserving slice with respect to the given tests. We have implemented two approaches of semantic history slicing, C-slicer and definer. They offer different trade-offs between efficiency and precision. C-slicer identifies a set of commits essential for passing tests based on static dependency analysis. It provides no guarantee for the size of final history slices, thus may be imprecise. However, it only executes tests once, so it is efficient. Definer performs the divide and conquer style history partitioning and reduction. It iteratively partitions history and runs tests on the partition until the slice becomes one minimal. Although it guarantees one minimal slices, the iterative execution of tests may be inefficient. However, this recent work have two limitations. The first limitation is the existing techniques have to compromise either efficiency or precision. But one interesting question is, would combining these operations lead to higher efficiency and precision? The second limitation is, existing techniques are inflexible in the sense that they cannot change the granularity of history. Another interesting question we can ask is, would finer-grained history improve precision? To remove these limitations, we propose GenSlice, a generalized history slicing framework. GenSlice abstracts existing approaches and splitting operation as transformation operators. Splitting operation means breaking down original commits to file-level changes to produce finer-grained histories. We use C for C-slicer, D for definer, and S for split. To explore different sequencing, GenSlice applies these operators in a loop style. Each run of the loop is a transformation sequence. For example, sequence C, S, D means first running C-slicer, then splitting its result, finally running definer on top of the splitting result. With different orders and occurrences of operators, GenSlice can explore any operations of semantic history slicing. We focus on two main aspects in our evaluation. First, we want to measure precision improvement of the optimal sequences over non-optimal ones. Second, we want to compare the efficiency among the optimal sequences. We take our evaluation subjects from the DOSC dataset, which is the dataset for semantic changes in version histories, published at MSR 17. In DOSC dataset, each functionality is uniquely identified by an issue ID on Jira, accompanied by a set of tests. Our subjects include 28 functionalities from 9 open-source projects, including CommonSlan, Flume, Maven, and PDFbox. To conclude, we present GenSlice, a novel framework that abstracts existing history slicing techniques and operations as transformation operators, which can be applied sequentially in various orders. We studied and proved the properties of several operator combinations. We reported an empirical evaluation of GenSlice, demonstrating its effectiveness on a set of real-world case studies and highlighted the most efficient sequences.